Hi, my name is John.
And my name is Alice, and you're watching Math Videos for Parents. We help you so you can help your kids with math. So today we're going to be talking about simplifying a radical when the index is greater than 2. But before we dive into that, John, I just have to comment on your wonderful math shirt.
Thank you. It's a holiday shirt with exponents. Fa la 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 la. There's 8 laws, sort of like multiplication. So it's law to the power of 8.
So if it was a radical with an index of 8, we could take the law out. And we can loop back to that at the end of the video.
Exactly. Let's do it.
Okay, wonderful. So to start, first I just want to kind of talk through our title here, simplifying a radical with an index greater than 2, because that alone can seem a little intimidating. But if we just break it down, the radical, that's just this square root sign. And then the index is this number here. If there's no number there, it's a 2. In this case, though, there is a number there. It's a 3, which is why it's greater than 2. Simplify, obviously, we want to make it as clean as we can. So I'm just going to dive in and do this problem. And John, I've got to say, I'm really glad that the number under the radical is 125, because what I need to do is I need to ask myself, what number times itself 3 times is going to give me 125? And I know that because I had to memorize it when I was a student. It would be 5 times 5 times 5 equals 125. So I can rewrite this to be 5 times 5 times 5. And the reason it has to be multiplied by itself 3 times is because the index is 3. So because I have 3 5s under that radical sign and the index is 3, that means my answer is 5. Again, I have that memorized. If it was something else, I would not be able to use this approach.
Yeah, that's great. And I learned it the exact same way. If we want to look at it a different way and tie in some of the stuff we talked about when we simplified radicals with an index of 2, we can use the prime factorization approach. And what that means is we look at the number 125 that's under the radical, and we try to decompose it into prime factors. Most students know that some of the smallest primes are 2, 3, 5, etc. And at first glance, since this is an odd number, we don't want to try dividing by 2 because that's not going to get us too far. 2 doesn't go into an odd number evenly. We could try dividing by 3, but that also won't work. There's a nice little trick you can use. If the digits themselves add up to a multiple of 3, then the number is divisible by 3. Because these add up to 8, which is not a multiple of 3, then 3 is not going to go in. So 5 is the prime number we want to try. And most students know that off the bat, because if the number ends in a 5, that means 5 is a factor of the number. So we can start by...
Or, John, if it ends in 0, right?
Or if it ends in 0 too, yeah. Yep, we can definitely try 5 as well. So we can start by dividing 125 by 5. And when we do that, we could think money, like $1.25 is 5 quarters. 125 divided by 5 is 25. So we have one prime number ready to go. Then we have to just factorize the 25 into prime factors. And luckily, 25 itself is a perfect square. It is equal to 5 times 5. So I can rewrite the 25 as 5 times 5. And at this point, I'm in the same place Alice was. I now have 3 5s underneath, a product of 3 5s. And for every 3, since my index is 3, for every 3 values I have underneath in the product, they come out as a perfect cube root. And there's nothing left inside. We took everything out. So technically, we divided it all out, and we get out 1. So there's nothing really left in there that'll impact the solution. So my answer is 5. We can also look at this from a geometric standpoint. With cubing, we can think of a cube itself, and 125 could be the volume of a cube whose side length is 5 apiece. So that ties in, we spoke previously about area models and rectangles and squares and things like that, but we can also take that concept up and move it to 3-dimensional figures as well. So this cube that I drew here, its volume would be 125, and that comes from side lengths of 5 and 5 and 5 apiece. However, something tells me not every problem will be as clean as this one.
What would be the fun in that, right? So the nice thing about this approach, John, is that we don't have to rely on having things memorized. And one thing I noticed as you were working through it that I should keep in mind was you were very careful with your notation. And you can see, wasn't over here. I wrote equals, but I really should have that radical and the index of 3. And that's just really good math form so that you always know exactly what you're trying to find. So I'm going to keep that in mind when we tackle a tougher problem.
All right, great. I look forward to the more difficult problem on the next slide.
Okay, so for our next problem, now we're looking for the fourth root of 90,000. And I'm excited. So what I'm going to do is I'm going to be careful to keep my notation correct. The index is 4 in this case. I'm going to break down 90,000, and the first thing that comes to my mind is 9 goes in. I'm just looking for the easiest ways to break this number up. Okay, so now I'm going to say, not there yet, of course. 3 times 3 will get us 9. And then for 10,000, I could say, well, 100 goes into it 100 times. Okay. So now the 3 is already prime, so it's just going to come down. And the 100, I'm going to say that's 25 times 4. And of course, the same for this one. And I'm just going to keep breaking it down until I'm to a point where I only have prime numbers. So the 3's come down. 25 can be split into 5 times 5. 4 can be split into 2 times 2. 25. It's like hanging wallpaper where it gets more and more off kilter. 5 times 5. And then 4 way over there is 2 times 2. Okay. So now I'm down to only prime numbers. I'm going to look carefully at this index of 4. And I'm going to look at each number and ask, does it show up under the radical at least 4 times? So there's 1, 3, the second 3. And I don't have any other 3's, so I can't pull a 3 out. So I'm just going to start building my answer over here. I'm going to be left with 3 times 3. And then I'm just going to cross these out to kind of tell myself I kept up with them. Now I'm going to look at the next number. I've got 5. And I have 4 of them. So because I have 4 5's, because the index is 4, I can pull out a 5. And I'm just going to cross these out. Now I'm going to look, and I've got a 2, a 2, a 2, and a 2. I've got 4 of them. So I can also pull out the 2. Let me give myself a little more space here. So I'm going to pull the 2 out. So I'm left outside the radical with 2 times 5, which is 10. And then inside the radical, I'm left with 3 times 3, which is 9. And one thing I could have done, I could have multiplied all these numbers together to make sure I got the 90,000. It's just a nice way to check your work. You know how I love checking my work. So, John, what are your thoughts?
Very understandable. And even though the numbers got pretty large, I feel like there's a procedure in place, and it's easy to take a number and break it down to a prime number wherever possible. And it's good to know that you don't need to have a perfect number underneath too, that if you don't quite have 4 of the same, you can just leave those numbers behind. Or if you have, like, let's say 5 of the same, you could take 4 out as one and then leave 1 in. So just having that flexibility is important. Kind of like on my shirt, right? Like, so if I have fa times la to the eighth, if I were taking an eighth root of that,
as you do,
as I always do, yeah. So there would be, there would be 8 of these. I'm not going to write them all out. It'll take a long time, but since there's 8 of them,
8 laws, right? One fa, 8 laws.
One fa, 8 laws, because there's 8 of them. I could take it out as a perfect, 8 when the index is 8, and I would have a lot on the outside, but because there's only one factor of fa and not 8 to take out, that would have to stay on the inside. So just a fun little twist.
I feel like we should make a shirt about that.
We should.
All right, wonderful. Well, thank you everyone for joining us. Please do send us your problem requests. You can just, if you have a math problem you're struggling with, just take a picture of it, email it to mathvideosforparents@gmail.com. We'll get back to you right away. Or you could leave a comment at our YouTube channel or on our Facebook page at Math Videos for Parents. Thanks so much.
Have a great day.